Hello, this is the second of the Proof by Induction videos for OCR Pure Core AS Further Maths. In this session, we use induction to prove results about matrices. If you have not already covered the matrices topic in this syllabus, you may wish to do this before continuing this video. Induction can be used to prove results about matrices, but often this involves proving a result about power of a matrix. For example, prove by induction that the matrix 3, 1, minus 4, minus 1 to the power of n equals 2n plus 1, n minus 4n minus 2n plus 1. Here's a quick reminder of what we covered in our previous video, which are the 3 steps for mathematical proof by induction. If you need to read these through again carefully, please pause now. Let's start with step 1. We need to consider n equals 1. Therefore, we're looking at 3 minus 4, 1 minus 1 to the power 1, which of course just equals 3 minus 4, 1 minus 1. And we need to see if we can write it in the same form as is given above here. So, we know n equals 1, so we can write 2 lots of 1 plus 1 as being the equivalent of the number 3. We can write minus 4 times 1 as being the same as minus 4. 1 is just 1. And here for the minus 1 value, we can write minus 2 times 1 plus 1. We have thus shown that this is in this form, 2n plus 1 minus 4n, n, and minus 2n plus 1 when n equals 1. Hence, the result is true for n equals 1. Moving on to step 2, we will assume that this is true for n equals k. Therefore, the assumption is 3 minus 4, 1 minus 1 to the power of k equals 2k plus 1, k minus 4k minus 2k plus 1. So that's our assumption. We're now going to consider n equals k plus 1. It's probably worth thinking at this stage about what we're trying to prove, and you may wish to do this in another part of the page. So what we're trying to do is to show that 3 minus 4, 1 minus 1 to the k plus 1 is equal to 2k plus 1 plus 1 minus 4k plus 1 k plus 1 minus 2k plus 1 plus 1. As I say, you may wish to put that as a scribble somewhere on a different page so you know what you're aiming at. But this doesn't, at this stage, making that statement is not part of that proof. That's what you've got to get to. Okay, so what you would actually write in your proof is that for n equals k plus 1, the matrix for power of k plus 1 will equal 3 minus 4, 1 minus 1 times 3 minus 4, 1 minus 1 to the power of k. Doesn't really matter if you pre-multiply or post-multiply. I've chosen to pre-multiply the way I've done it. However, we know that this here is the matrix to the power of k, and we've already made an assumption about that. So I'm going to use that assumption just as I did in the previous video where we were looking at a series pattern. I use that assumption. So I'm going to assume, or sorry, use that assumption, 2k plus 1 minus 4k, k, and minus 2k plus 1. So I've swapped in my assumption for n equals k in place of this matrix up here. Okay, so let's multiply this out. I'm going to have 6k plus 3 minus 4k minus 12k plus 8k minus 4, 2k plus 1 minus k, minus 4k plus 2k minus 1, just using normal matrix multiplication. That gives me 2k plus 3 minus 4k minus 4, k plus 1, and minus 2k minus 1. Because earlier I wrote out what I was looking for, I can more easily see the form to now write this in. So I'm going to write that as being 2k plus 1 again, minus 4k plus 1, k plus 1 can stay as it is, and minus 2k plus 1 plus 1. You may wish to take a minute to check my working and also to consider whether that is actually in the right form for what we're trying to show. Again, here in summary, we can see that if our assumed result was true for n equals k, we have shown that it is also true for n equals k plus 1. So that concludes step 2 of the mathematical proof by induction. It is important not to forget the concluding step, step 3. We must make this type of statement for every question, however boring it gets to keep writing it out. So, if the conjecture result is true for n equals k, then it's also true for n equals k plus 1. As the result is also true for when n equals 1, it must therefore be true for all integers, or you can use natural numbers, n greater or equal to 1 by mathematical induction. In session 2.3, we'll use induction to prove results about divisibility, and we'll therefore be looking at the whole process again in a slightly different way.